And folks in the room, can you hear okay? All right.
All right. So, uh, sort of set the stage. My wife and I tore down a house we'd lived in for 31 years in order to build a home to age in place. And this was a little bit of an interesting discussion because as I broached the subject with my wife, she said, "Over my dead body." Uh, we had known we needed a house to where we could age in place in because the old house had lots of problems. So I think at my core, I'm a systems engineer, engineer complex projects. And so I think it's important that we go back and start a little bit from the beginning here. If you if you think about a house, um, since really the dawn of civilization, humans have sought shelter from the environment, and they really need an interior that would allow them to thrive. So I think understanding that thriving is a key objective. It's important to put that as a highest level objective function. It seems like I need to give the slide uh, an engraved invitation to change. So here's the house is finished, and it was certified by FIAS, which is a Passive House Institute of the U.S., to meet a new standard 2021, which was supposed to be which is a net zero standard. Now it has been recognized already by the Green Home as a Green Home of the Year by the Green Builders magazine. The U.S. Department of Energy awarded it a Housing Innovation Award. Now, this was not the only, there are a number of those projects in any given year. And the Michigan Efficient Energy Construction Association named it their project of the year. Now, as I mentioned, thriving is really important, and I would choose to define indoor air quality as crucial metrics. This is a picture of a View Plus made by a European company, AirThings, and it monitors a number of components of indoor air, and I use it to ensure that the interior of the house is really important and we're able to thrive. Now, the other thing that's really important, if you think about a home, you'd like it to be very cost effective to operate and use a minimum amount of energy. This is a picture of a model that the builders had to build to ensure they knew what they were doing. Actually, it's a shortened version of a whole wall assembly for 2 stories. And really what's important here is it's a double wall. The green layer, which is a vapor barrier, is on one side of a OSB, and then there's insulation on the outside of that, and then there's also insulation on the other side. Walls are about 12 inches thick, and they're set up this way so that they can dry from the inside out and never really pick up moisture. And so the energy efficiency is where we wanted to start. And then if future generations are going to thrive, the energy to power the house at a minimal level needs to be generated by renewable resources so that future generations can thrive. And this is a picture, if you're to count them all, there are 47 solar panels there. So if we stop and look, here's another shot at the wall. The double wall construction, the walls are R49. They're, 2x4s on center, 24 inches on center, fiberglass, the OSB. And I think the other thing that's important to note is that anywhere there's a nail in the OSB, it was sealed. And that's important for a later part of the discussion. But this house they spent an extreme amount of care making sure it was sealed. Gable trusses, the attic is got blown-in insulation. It's got 120 R value. The foundation was done in a very unique style called insulated concrete forms, where you need to think of blocks of styrofoam like Legos that were separated by a plastic lattice, and then concrete was poured in between those, so that the foundation is R54, and then the windows are triple pane, really well insulated windows. So here's an aerial view of, and now we're going to talk about some of the systems. And the first one I want to mention is the ventilation system. The ERV stands for Enthalpy Recovery Unit. And then the HVAC are ducted mini splits. And there's the solar panels nominally will generate about 21 kilowatts. And we've got battery storage of 45.6 kilowatt hours. So I just mentioned 45.6 kilowatt hours of lithium ferrous phosphate batteries, manufactured by a company at the time was Simplify. Simplify has been acquired in the last 18 months by Briggs and Stratton, and Briggs and Stratton has rebranded that company as Briggs and Stratton Energy. The heart and soul, and I'll show you a picture of this later, is an inverter, and really a couple of inverters manufactured by a Texas company called Solarc, and it's a Solarc 15K inverter. And I'll talk a little bit about that some more in the next slide, and on a later slide. So I've sort of run through, the lithium ferrous phosphate is also known for safety and longevity. It's a very thermally stable compound. Urban legend has it was developed and initially used for people that were living off the grid in Alaska. I don't know if I believe that, but this company was also selling them to FEMA so that FEMA could put them in the sea containers and drop them into disaster area, have instant power. Then the inverter is nominally a 15K inverter, means that's all the power it will feed into the house. It can manage more than that. But fundamentally, the solar cells are operating, say, 200 to 240 volts and up to about 20 amps. And so you've got to take that direct current and convert it to 120/60 to run the house. And then you charge the batteries anywhere from 48 to 56 volts DC. So you need to go from 120/60 to 48 to 56 volts. And then the batteries give us a lot of flexibility. It's sort of interesting. Originally, the utility that serves southeastern Michigan is not very reliable. And we previously had a generator that was fueled with natural gas, and I decided, we aren't going to do that. So I asked my wife, well, how many days should we operate if the utility goes down? And we decided on 3 days and did all the calculations and said, if, we really reduced our load, how much capacity we would need. And I came up with a 45 kilowatts hours. And then it had dawned on me, you could run this house at night during the summertime on the batteries. And so that now has created a tremendous amount of flexibility. So I mentioned the house was net positive. This is a screenshot from the website that the Solar is connected to. And you can see in 2023, we moved into the house in May of 23. And you can see red is where I bought power from the utility. And green is where I and green is where I sold it. And then in 24, we were more net positive. And you can see I'm starting in the hole, which I was in the hole last year quite a bit because of January and December. And we're beginning to dig out. The next slide will show you what happened over the course of 2024. You can see in January, I didn't generate anything. Actually, I was slightly net positive in February. It'll remains to be seen whether I can duplicate that. And then, in May, I didn't buy any power, and in June, I didn't buy any power. And then as the summer came along and the electrical loads got higher, it became more substantial. The big piece here, though, is for the last 12 months. So think February through this January 25, my total electrical bill was $379. So in terms of being economically, operationally, and I think we're going to get it below that. Now, I mentioned that all those nail heads were sealed. And what's important there is houses leak, and they leak air with not very much pressure. The standard test to evaluate a house for air leakage is air exchanges per hour. So the house is put under a very slight vacuum, 50 pascals, and then they measure how much air leaks into the house. Now, let's put pascals in a frame of reference. Early in my career at GM, I used to calibrate engines, and we use kilopascals as a pressure measurement. It's a metric pressure measurement. And it was very useful because conveniently, sea level is 100,000 kilopascals. And so, 100 kPa was what we referred to at sea level. And, if you went into Denver, you were operating at 85 kPa because you were at 5,000 feet. So it was really convenient. But this vacuum that the house is under is not kilopascals, but pascals. So the FIA standard that we had to meet to be certified was 0.6 air exchanges per hour when the house was at 50 kilopascals. When they tested this house, it was 0.269, so well underneath the standard we had to meet. And the certification technician that brought his blower door in to measure it said it was the tightest house he'd ever certified. So now, why is that important? And for the next piece, and that is an enthalpy recovery unit. Because if we lived in this house and never opened the doors or windows, we'd run out of oxygen. So we have an ERV, and here's sort of a schematic of what they are. But you bring fresh air in, goes through a purifier, in our case, a MERV 13 filter, goes through a heat exchanger. And they make two different classes of these. And, the thermodynamics background in me drives me crazy because one of them is labeled as an HRV, meaning heat recovery unit, and the other one's an ERV. And the difference is ERVs try to deal with latent heat, and they have a porous membrane where moisture can go back and forth. You'll find some people refer to these as energy recovery units, and the other variety as heat recovery units. But that's why I say it. Their definitions drive me crazy as a purist. But in any case, you get fresh air introduced, and then in bathrooms, in kitchens, the exhaust goes out through the other side. And here's a better picture of more detail of what's really going on there in terms of the fresh air and stuff, even though it doesn't show a lot of moisture getting transferred through this porous membrane. Here's a picture the white box Zender is the ERV is manufactured a company in Netherlands, and the Europeans have been doing this for a few decades. There are a couple of American companies that are doing it now. And so we've got to distribute the air throughout the house. And then the other units you see are actually air handlers for air-to-air heat pumps that provide our heating and air conditioning. Um, and I'll show you a picture of those in a second. But those are, and then this unit, I'm assuming you can see my cursor. That's a dehumidifier that we run during the summer. This unit right here is actually a humidifier because last winter the house got exceedingly dry, and we had to fix that. And if you look at the air quality standards, particularly after COVID, you want the humidity in a house to be between 40 and 60. Some people would say 30 and 60, but there's a doctor, Stephanie Taylor, who does a lot of work with ASHRAE, and she's got a lot of videos out there. And interesting, a medical doctor that went back and got an architectural degree because she wanted to understand a lot of this. So you want to have continuous air, energy recovery, and then improved indoor air quality because they've got up in here, there are a couple of filters, and the incoming air goes through a MERV 13 filter that takes even very, very small particles out. And this is a shot of the outdoor side of 3 air-to-air mini splits that are cold air. You know, we've had some cold mornings up here last couple of weeks down to -12. We're fine. Now, full disclosure, when you get to -12, these things use lots of power. Think 7,000 watts. But they're really efficient. You know, the majority of the time they don't use that much power. It's super comfortable, and then it's certainly really a eco-friendly choice. So here's our certification plaque from FIAS. We were the first house designed certified in the U.S., second house because of COVID and everything that actually get to final certification after all the inspections. So really, the comfort of the house, there's no draftiness or anything, and clearly it's very sustainable. I mentioned we keep track of indoor air. This is a shot. I have a number of different sensors. I have 4 of the more complex sensors and then 3 more simpler ones. But we look at radon and particulate matter are both at 1 and 2.5, carbon dioxide, volatile organic compounds, humidity, temperature, and pressure. This volatile organic compounds is interesting. Well, a lot of it's bad. When we come back from the farmer's market with a bag of peaches, I found out that they gave off a lot of VOCs as well. And depending on the time, there's a really interesting insight. Well, radon is a gas that occurs naturally in the soil in Michigan, and we all have, any new construction has to have radon mitigation systems in it, and ours certainly did. But the sensor in the basement all of a sudden picked up radon. And it was last January when it was very, very cold. And I thought, oh, what's going on? Maybe the traps in the drains are dry. I poured water in and still no avail. And then I started reading about radon. And when it gets really cold, the top layer of the soil freezes and it can't get out. And we had some window wells in the basement. And I theorized that maybe the soil was warmer and it was leaking into the house around the seals because the windows were pressurized. So the ERV can add a number of different settings, and I'm actually running the house very, very slightly positive. And when I took the house positive, the radon disappeared. So it was the fact that there was enough pressure building in the window wells because of the frozen uh, soil that and we have covers on the window wells to keep squirrels from falling in, and there's a load of snow in, so I think they were pretty well sealed up. And here you can see, just I can look at it on a various time scales and just what happens, and you get a sense for how tight and where the levels are. So, you know, really comprehensive, all of the organic compounds, particulate matter, radons, and CO2, really important when you stop and think of. So, you look, we've got awards, and the housing award their criteria was, you know, for the energy efficient, but innovation and the sustainability efforts. We go through rigorous indoor air quality measurements. And then I think there's a lot of, we did this, that we called a house a pleasant future valley vision, because we really did this not only for our own aging in place, but to create a model and to be able to do lectures like this. So net positive, supporting aging, and I didn't, because of time, I didn't talk about, all the things, the big wide doorways and, not steps and stuff like that we've done, and the sustainable design. So with that, we can talk questions or go to your next presentation, whatever you guys want to do.
I think some Q&A would be great. Thank you so much. That was a fascinating talk. I guess we'll just open to students in the room, and I'll just paraphrase your questions so that Harvey can hear them clearly.
Yeah. My first two are like, would you ever like sell the blueprint, and then how much does the whole thing cost?
Okay, so two questions are, one, would you sell the blueprint? I guess if somebody wanted to build their own version of it elsewhere?
I don't know. Quite frankly, I don't know what the legal requirements for that are, whether or not the design actually belongs to the architect. The architect is a guy named Michael Clement in Ann Arbor, and I actually found him, even though he's in Ann Arbor, through a webinar. He has built, THEIS is probably the second most stringent building standard in the nation right now. It's more stringent than any of the LEEDs. There's one more building standard, more stringent, and that's a living building challenge. And you can't even have a styrofoam cup on the build site. And he did a home outside of Ann Arbor, Burbeck is the name of the home. And then there's another one that was in Bend, Oregon. I think now there are a few more homes that meet the living building challenge. My assumption, I don't know who actually owns the prints to that, but the wall construction technique, I think, is something that building science, this guy, I think his name's out of Boston. First name's Joe and got a long Polish name, that talks on a lot of YouTube videos and stuff about this. I don't think all that stuff is all that tough to come by. What's hard is, I think, the rough framing crew that did the job, that took an immense amount of pride. I remember we had some preliminary blower door tests, and these guys running around looking for leaks, like, you were challenging their work, and they the amount of pride and dedication they had in doing this, I think would be the bigger challenge. And I'm going to pass on the cost.
Fair enough. And
But
yeah,
I would tell you, you asked for things that people could sink their teeth into. I would suggest that we probably spent roughly $90,000 on the battery and the solar cells and the controller and everything. There, you ask about assignments and challenges, so there that gets baked into one.
Okay. Yeah, fair point about having skilled craftspeople who really take that level of pride in their work. I think that's really hard to find with builders, so that's very cool. Other questions from there? Yep.
Um, so if you mentioned like super cold, and heating gets really expensive, has he considered thermal energy storage?
So the question is, the mini splits the heat pumps use a
Mm.
lot of power when it gets very cold. Have you considered something like thermal energy storage to do basically shifting of the heating load?
No, quite frankly, the house next door has a geothermal, and the friends of my sons have geothermal. Uh, and the one next door has lots of pipes and valves, and they've always got repair people in there. So I was not interested in doing that. Now, whether or not um, that's a good choice. Uh, Originally, when I went into this discussion, I wanted to do geothermal. The architect talked me out of it. Um, Now, but the number of days that I'm dealing with, anything below zero is probably I can count on one hand. And then I'm still going to be net positive.
And the 7 kilowatt number that you mentioned for the heat pumps, was that for each unit, or was that combined over all of the three mini splits?
No, when if it's been cold, so turn the temperature in the house down. Uh, Two of them are off during the night altogether, and then during the middle of the night, I turn one down to 62 degrees. When it starts in the morning, it goes into a defrost mode and then powers up. It powers up at about 7,000 and then will drift down to 5 until the temperature of the ambient goes up. Um, Now these are Mitsubishi Train. They're made, I think, down outside of Atlanta, a joint venture between Train, I think is out of Minneapolis, and Mitsubishi. Um, but I think they're probably sort of the leading edge of the market, and people are trying to catch them right now.
So are those do they have indoor heads that provide heating, to specific rooms, or is that like a central system they supply air?
No, no, they're the picture I showed with the mini when I showed you the ERV down in the basement, those other boxes were air handlers. So that's central heat exchanger from the outside is inside that, and then you think of it as a normal forced air. Now they make um, mini splits that exist on a room. The the range of selection of mini splits, I've been somewhat shocked and impressed with.
Does he have any kind of like a water system, like gray water is just totally normal water system?
So the question is about water sustainability. Do you have things like gray water catching and recycling, or what have you done on the water side?
Well, I specifically didn't put that in, but over my shoulder, if you look at the picture over my shoulder, you see those black circles there. So one of the things our highest utility bill was water.
Oh, wow.
And that's because we have, even though the house is not that big, historically in the city, we have a big lot. And the stormwater runoff into the sewer, we have unfortunately a combined sewer stormwater system at this portion of the city. And so they do an allocation of costs based on your area, and then they try to do a determination between permeable and impermeable soil. So in an effort, I wanted to sink a well so that I could irrigate. And then the city engineer says, no, that's not good for the aquifer. And you should keep, so we capture the water and we retain all the water on property. Now those black circles are openings. There are three 1,500 gallon cisterns. So all the water from the roof and it gets pumped into those cisterns, and then we do the irrigation from those cisterns. Now, we don't have a gray water system in terms of a traditional gray water system.
Thanks. Maybe a couple more questions from the room, Joseph.
I was just wondering about climate change adaptation. Is there anything you sort of took into consideration, whether that's like flooding or forest fires or whatever, that might be affecting the area, or is it too up in the air?
So the question is around climate change adaptation. So you mentioned lots on the sort of mitigation side of reducing emissions and providing sustainable energy, but what about adapting to things like wildfire risks or changing rain and water patterns, things like that?
Well, the from flooding, we're probably pretty insensitive. There is a small river that goes within about 300 yards of the property, but we're up about 150 feet above that. And there are floodplains further downstream that are set up. There's a nice, huge, flat golf course that's lower than we are. So it'd take out the whole golf course before it even approached us. But the other interesting thing, during the summer of 23, when we had all those Canadian forest fires, I was changing the ERV filters about once every 3 weeks because they were capturing, and it was shocking to me. I had no idea how much this stuff is floating around in the air. And it's just been so I would tell everybody, they need to be thinking about how to manage forest fire smoke. Even the Canadian stuff was, some of it I think was 1,000 miles away from us. It was coming in and coming across the Great Lakes.
Yeah, I had a similar experience living in Massachusetts, several years ago when there were wildfires on the West Coast, and yeah, we were getting wildfire smoke literally 2,000 miles away. So, very good point. And I guess as you guys know, most residential buildings don't have any kind of air quality assurance, right? So no filtration, no intentional ventilation. We just rely on kind of passive air exchange with the outdoors for freshness. So, okay, maybe one more question from the room if there's one.
Yeah, could you talk about like the concept of age in place and some other strategies that you did with that?
Yeah, could you talk about the concept of aging in place and some of the strategies that you did around that?
Sure. Well, my wife in her first career was a physical therapist. So one of the things we want to make sure of is if we were ever in a wheelchair or a walker, and actually a walker could be a little bit more concerning. But most of our doorways are all pocket doors. And the other thing is where they can't be pocket doors, they're split. So all the doors are 36 inches, but that door swing is problematic. And so they're split into two and they split open. I can probably go find a picture here real quick and share it in terms of that. And then all the steps that are exist are short, and so that's the other thing is really ensuring that the steps have got capability so that you could move through them easily without having any significant problems. Or would also be a key along the way. So let's see. And then probably the big one that is shocking is an elevator. Now, because we had to put the house in a proper position for the solar panels, then we had to set it up so that uh, the okay, let me see if I can shoot. So we had to get this. We needed a first floor bedroom, but we needed to be able to get to the rest of the house. So we ended up having to put in an elevator, and we made a pact with each other. We're not going to use it um, until we absolutely have to. But our dog is old, and we had to set it up for the dog to get up and down. Um,
Harvey,
and I
in the interest of
okay.
time here, maybe I could ask you if you have any. Oh, you found it. Okay, great.
Well,
Um,
this is not the picture I wanted, but I was going to show you the picture that the installation downtown, down in the basement of the solar, the batteries and the solar. But I don't know if you can see that or not.
not,
Right.
no, we can't really see it in the room.
Yeah, okay. So you're probably, I well past the time limit here.
Yeah, we're going to stay a little bit late for our second speaker, but I guess just in closing, maybe you could sort of tease a couple of ideas of maybe unsolved problems that you still have or projects that you think might be really interesting.
Well, so there are a couple of ideas I would have. So I'm still trying to learn how to operate this house optimally. So the balance between when I use energy from the balance of the batteries and when I charge the batteries, and I've got a time of use, a dynamic peak pricing program that compensates me differently. So I have data for every 5 minutes, I think, for the whole 18 months I've got here across all sorts of data that comes out of the solar. It's all CVS. I could set that all down. Somebody could figure out if I'm doing things wrong or so that's a big one. The other piece is the Public Service Commission has recognized in the state of Michigan that they don't electrical needs in the state are going to be astronomical over the next 5 years. You can't build enough central distribution power plants fast enough to meet the need. So they're looking for a way to come up with parameters for a virtual power plants. So if you were to take a nominal cost of the system of $90,000, the utility gets compensated at a 10% rate for their capital investments. If all the residential, municipal, school districts were to get some form of compensation in that manner over 30 years to give them a 10%, how much money would I need to get on an annual basis to hit that 10% to be equal to what the utility gets, and recognizing part of my compensation is not paying an alternative uh, time of use program. So you'd have to look at the alternative time of use versus mine versus I'm being undercompensated because I'm getting compensated for the power I sell from what they can buy from MISO, and that's doesn't get me close to 10%. So those are a couple that I got.
That's great. Thank you. And some of those terms may not mean much to you guys yet, but within the next like 4 or 5 lectures, we will talk through what these different pricing plans and kind of utility interactions and things like that look like. So thank you, Harvey, so much for the talk.
Okay.
And is it okay if some students, if they get excited about a project or just want to
Sure.
with you, can they reach out?
Yeah, that's why I keep flunking retirement is I work with all the student teams at Michigan. Think Solar Car, Formula SE racing teams, and Baja. Uh, that's what keeps me going. So I'm happy to talk to students anytime.
Flunking retirement. I love that idea. Great. Well, thanks so much.
Okay.
Okay, so I'm going to introduce our second speaker. Harvey, you are welcome to hang if you would like.
Hang in there.
Okay.
I'm going to put myself on mute.
Great, thanks. So I think that was a really fascinating presentation about what what the best you can do is really in terms of new build residential construction. Our next speaker, Erich Moraine, will talk to us about an energy retrofit project that he and his wife have been undertaking for several years now to basically rebuild an older home, I think 1800s era home. So I'm excited to hear about kind of the comparison, the juxtaposition between the new build and the renovation case. So Erich, why don't you come on up? I'll set you up with your slides and screen share here.
Excellent.
Um,
Perfect.
Good.
All right. Yeah, so this is I really appreciated Dr. Bell's presentation because there's a lot of stuff that he's done that I've also spent time thinking about. There are common problems in home renovation. My wife and I now live in the house that she grew up in, which was homesteaded by her grandparents. And we're guesstimating approximately 1870. Nobody actually knows exactly. There were a number of renovations. This is the oldest photo I can get of it. This is what it looked like pre 2021 when we kind of bought into the idea of we need to do something. This is what it looked like, more or less done. You can still see there are a few ladders standing around, but a significant difference between the outside and the inside. The curb appeal went up by a fair amount. So the project overview, we were motivated. We had to do something. The roof was leaking. There were 3 layers of shingles, 1 layer of cedar, 2 layers of asphalt, and everything was rotting through. I had a vintage furnace. Some people pay extra for vintage. Yeah, I did not. So we got a 1980s vintage natural gas furnace converted to burning propane. And every year I had to get down on my hands and knees and pray to the furnace goddess that it would run another season. We had a leaky basement. We had pet salamanders living in the basement because of the amount of moisture down there. So it really wasn't usable for any kind of storage. And ultimately what happened was I lost my homeowner's coverage because they made a surprise inspection. They said, absolutely no way we're going to cover you for anything. So it was, the knife was at my throat. We really had to do something. So we were trying to figure out old versus new construction. The original idea, it looked real cool on paper. Let's tear down the old one and build something new in the backyard. We got about 3 acres, so there was plenty of room. And it took about a year and a half working with a contractor and spending a whole bunch of consultation money with an architect until we kind of figured out there's no chance that we can actually afford that. So we were looking at right now the current cost for renovation. I'm projecting to end up at about 235K, which is roughly $117 a square foot. There is no chance you can build a house for $117 a square foot. The estimate for the new house, which was not fixed in place, didn't include appliances, internal furnishings on the high side of $500,000. And it would have been roughly 2,700 square foot. So we're looking at $185 a square foot for a new construction. We were kind of aiming for passive house. I was really excited to hear Dr. Bell talk about it. I think it's an awesome metric to try to hit. And it's reasonably expensive to get there. So when I figured out what the new construction was going to cost, then I also started to kind of recognize there's embodied energy in the existing structure. And yeah, the basement is wet, but it's 16-inch thick fieldstone basement walls. It was a bit drafty, let's just say, but the lumber was virgin pine with actual 2-inch by 4-inch 2x4s, which you cannot buy today, no matter what you're willing to spend. So the quality of the materials it far exceeds what you can find conventionally today. The structure, the bones of the house were really solid, but it needed a little bit of a facelift. So we were hoping to try to meet passive house standards. There are varying standards. So there's a slightly lower standard for a retrofit, for a renovation project, but it still would have been challenging and would have added somewhere around $6,000 to the cost of the project to just meet all the documentation and certification process. So we started to look at a little more pragmatic solution, and I'm trying to figure out if I'm willing to give a little bit in terms of higher energy consumption, not quite as airtight, not quite as super efficient. Maybe I can help reduce the global planetary impact by retaining the embodied energy in the old structure without having to burn it to the ground, basically. So the decision was renovate instead of new construction. And then came the next kind of compromise solution, either build a really hotshot, amazing house or have money to retire. Because both of us are in our 60s, my wife and I, and so there wasn't enough room financially to do both. So again, we had to kind of back down just a little bit in terms of the construction ideals. Some of the energy, air tightness and things is really rather expensive to do and difficult or impossible sometimes to retrofit into an existing structure. When you're building from scratch, you can design some of those pieces in place, and that's not really possible if you're retrofitting and working with existing. Insulation as much as possible, absolutely, but there's a limit, and materials costs as well. We're looking at insulation and a variety of other things, and there's a cost benefit ratio there. And if money is no object, absolutely buy the highest possible R value you can get. I had to kind of live within a budget, and so we backed down just a little bit. And the most difficult one was contractor willingness. Can I actually find somebody, who's willing to do the work? And that turned out to be the biggest deciding factor. I went through 9 or 10 contractors in the area. There would have been an architect out of Chicago in Oak Park, which is a pretty high-end suburb, that would have been willing to take the project on, but I don't know that I could have even afforded his consult fee, much less the building he would have designed. So eventually we found a contractor who was willing to do it within limits. He was not willing to go to 6-inch thick insulation on the walls, but he was willing to try 4-inch, although he had never done such a thing before. Right? So we were really off the edge of the map in terms of what he was willing to do. High efficiency HVAC. I was delighted to hear Dr. Bell mention geothermal because I was all over that. I knew for years and years I'm going to have a geothermal install. And then when I figured out, when I started running the manual J calculations, the amount of power that I need versus the base cost for installing geothermal, it was prohibitive. My house would have needed to be triple the size. I'm looking at approximately 2,000 square foot. The base cost for hardware for geothermal just made it so prohibitively expensive, there's no chance. So I had to back off and settle for air-to-air heat pumps instead. I also went with, now I understand it's called an enthalpy recovery unit instead of energy. And then we'll ultimately be looking at an air source heat pump. The theoretical ideal is passive solar and or a ground source heat pump, geothermal, but that was just not going to happen given my budget. Pre-renovation details. What am I starting with? Zero air barrier. Right? The original exterior shiplap siding was taken off sometime in the 1950s. And so I have genuine vintage first generation aluminum siding that I was working with. Some sections of it were replaced with second generation, so it wasn't quite as chalky. There was some attic insulation, 2 inches of poured in vermiculite, which is expanded mica, the puffed mica stuff. And that has some health issues with it, but there was 2 inches of insulation in the attic, which was probably cutting edge for 1955. Not quite so much today. 1950s vintage single pane, double hung wooden windows with no weather stripping. So they rattle when the wind blows. And if I had candles on the kitchen table, you could watch the candles drifting back and forth in the air. The original heat was a wood stove in the kitchen with a large 24-inch square grate in the kitchen ceiling, which heated the upstairs. That eventually got replaced with an oil burner in the basement, and ducted air was retrofitted into the building. That oil burner got replaced roughly 1980 with a forced air propane furnace. And I'm estimating the efficiency to be somewhere on the low side of 60%. But there's really no way to know. The basement walls are 16-inch thick fieldstone handset. And I eventually learned that only some of that actually has mortar in it. The stones are just kind of dry stacked on top of each other. But the lumber and the basement was solid. Like I said, it's old growth white pine. It's really, really sturdy. When the contractors were trying to put up some of the roofing stuff, they had to resort to impact guns because they're electric screw guns. Even the Milwaukee Electric, packed full of testosterone, could not drive the screws into the roof rafters. They had to use impact drills. The pre-renovation energy performance, just as a starting point, Dr. Bell mentioned a blower door test. I had one done as well. He didn't really understand how to operate the blower door adequately. There would have been another restrictor collar he could have taken off, but he maxed it out at 4,950 cubic foot per minute and was only able to get it to 28 Pascal. The actual reference measurement is, as Dr. Bell had mentioned, 50 Pascal. So he couldn't get it up that high. So that produced an air exchange rate in the building of somewhere upwards of 20 air exchanges per hour.
And the passive test standard is like 0.6.
Yeah. So we're looking at 20 plus air exchanges per hour, right? So it's basically you've got a door and a few windows open all the time, right? My estimated propane usage was somewhere around 1,500 gallons a year of propane. So that's a pretty serious carbon footprint. This is what it looked like on the outside, right? That is the top layer of shingles. You can see the vintage aluminum siding. Everything was loose, everything was worn out, everything was rattly. There's the curb appeal that we started with, okay? So we had nowhere to go but up. This is the blower door test. You can see where we're at, negative 28 Pascal. You could not drive it down to 50. So we started at the bottom, right? This is the basement crew, my wife, and then this old guy that showed up one day, completely accidentally, and we struck up a nice conversation, and I looked at his hands and I said, "Sir, you are not an accountant. What do you do for a living?" It turns out he was a stonemason trained in Croatia, came over here at age 12, and he was willing to repair and renovate basement fieldstone walls. I ran out of contractors. Again, even looking at the ones on the websites that had pictures of fieldstone walls. No, we don't actually do that. We would take that out and replace it with a poured wall. I said, no, I've just got an old one that I need help with because this is old lime-based mortar, as opposed to the contemporary high temperature Portland cement, which is waterproof and humidity resistant. This was not, it crumbles. This is just what people had. So we started in the basement, and there he is, replacing some of the stones in places where they had literally fallen out of the walls. When this house was built, they dug a ditch about 4 foot deep, roughly the height of the ventilators. And as they're throwing dirt up over the edge, any stones they got, they literally stacked it up neat and tidy against the inside edge of the hole that they were digging. This was the basement wall. So some of that, let's just say, was a little loose, needed a little bit of help. And this is what it looked like when Louis was finished with it. He did a super job, and without him, I guess I would have had to figure it out because I couldn't find a contractor. It was not going to happen. So this is the exterior basement wall stabilization, which was a bit of a project. That's where I realized the mortar holding the walls together is only about down to 12 inches below grade. Underneath that, it's loose stacked. I was hoping to excavate. I rented a mini X and was hoping to excavate down to the frost line, which in my region, southeastern Wisconsin, just west of Milwaukee, is about 4 foot below grade. I started digging and the wall collapsed because there was nothing holding it in place except the dirt, right? So there's no mortar there. So we had to kind of reevaluate. So once he had done the external reevaluation and kind of renovation, kind of mortaring the stuff back in place, I started in with the thermal renovation, the thermal mitigation. So I put in a double layer of 2-inch polyisocyanate foam, which is rated for direct burial. Gapped it and sprayed it with great stuff foam. Also used great stuff foam to glue it against the exterior walls, which were a little bit rough. There was a second layer. They were offset. So I've got 4 inches total with offset staggered joints. And there I was working on trying to trim it up to get a little bit of a finished surface, the next step is the water mitigation because I didn't really want salamanders and frogs living in the basement anymore. So I used ice and water dam, which is meant for the first 3 foot around the perimeter of a roof line to prevent ice dams from building up. It's a butyl rubber, like 60,000, I think, thickness with a adhesive layer on the backside. So I glued about 12 inches of that up against the foam board, and then the other 24 inches was just laid down on the ground. To start diverting some of the waterway. And if you look in the distance there, you can see that white snake sort of in the ground. You can see it here on the left side as well. That's a French drain product, black perforated pipe surrounded by a 10-inch sleeve of screen, basically, and that gap in between the two is filled with styrofoam, star-shaped little chunks of styrofoam. So I could bury that in dirt. I did not have to put in crushed stone as an absorption layer. I could backfill directly with dirt. Off of the corners of the building, it has natural drainage. I trenched it in so that I don't need crock pot, drain tile, so it's natural drainage. So that's what it looks like when it's done. I got a little bit of a brick ledge on there, and the rest of the exterior wall insulation will now get built up on top of that. The contractor absolutely insisted on wrapping the house in Tyvek, which was a complete waste of money and time because it's stapled in place, right? This is about as airtight as a window screen. You can see some of the original wall there. This is actually 1-inch thick boards that are tongue and groove. They lock in place. And this is what's nailed on top of the 2x4s. This is a balloon frame style construction. So the 2x4s run from an 8-inch wooden beam that sits on top of the basement wall all the way up to the attic, continuous run. And the 1-inch thick, 8 to 10-inch wide boards are nailed around the perimeter, which made it really easy for the original carpenters when they decided to put in doors and windows. The homeowner would look at it and say, I want a door there, and the carpenter would just take his saw and cut a hole in the wall because the exterior is structural load bearing. It's really, really sturdy, quite solid. The roof did not survive so well. What looks like insulation along the lower right-hand edge is actually help from the local flora and fauna. They had chewed their way through the soffit and fascia, and there was a lot of squirrel nests up there. So now they're tearing off the rotted boards. You can see here they're starting to replace it a little bit. They'd cut off the rafter tails, which are the pieces of rafter that hang over the edge of the wall that will make the overhang. They'll have to get replaced a little bit later. This is what it looked like on the inside. And I think at one point they had some contests about how many ladders could they get in a 10 square foot area. Only once did somebody fall and get hurt, but it was a bit of a project. And there you can see the new rafter tails and some of the roofing construction. So I opted for more expensive foam board. This is double foil faced, 3 inches thick. And again, staggered offset joints that are backfilled with foam and then taped as well. So all the nail holes, all the seams are taped with aluminum tape to try to make it as airtight as possible. This ended up being a challenge where the rafter tails hang over and meet with the house walls. Ended up being problematic. And here you can see they sprayed it, the gaps with Great Stuff foam, and then that gets trimmed, and then there's either butyl rubber tape that goes over it, or there's another picture later on that shows, where are we at here? Sorry, that shows aluminum tape. On the left-hand side, you can see the layer of OSB, and that is what the shingles are going to get nailed down onto. So I had 6 inches of foam insulation on the roof on the outside. Here you can see the exterior walls before the foam starts to get applied to the exterior walls. Now you've got an old house with a new hat. So now they're starting to do the tear off on the siding. Eventually we'll get the windows swapped out as well. And it looks pretty normal from the street. You can't actually tell what's happening underneath the shingles, what's happening behind the siding, except that the walls are like 11 inches thick on mine, the finished construction. Here you can see they're getting started with the foam board. Here's a double layer of foam. Again, it's offset, staggered joints, backfilled with great stuff, spray foam, and then taped off. I kept telling the contractors, you're building a boat, right? Just making it sort of airtight is not enough. You're building a boat. It actually has to be so watertight that it would float. And he thought I was nuts. I also learned why he was the low bidder, because he would go down to the local job pool and hire day laborers to come in for the day. So there were constantly people getting retrained on how this is supposed to work, which ultimately produced a problem in terms of the quality of the fit and finish, the final installation, because there were folks that were brand new on the job. They had never seen or heard of such craziness of trying to make it this tight and make it that thick. So there were a few installation errors that eventually started to show up. And here you can see the foam is sprayed. You can see one of the screws there. They were running 12-inch screws back into the studs. It was so the boards here are battens that are going to ultimately be used to hold the LP Smart Side, which is a compressed OSB. It's a wood product, but it's lap siding. And that needs a solid nailing surface. But if you've got a 4-inch thick wall, what do you nail the siding onto, right? So the battens created about a 3/4-inch air gap behind the siding to allow for natural air movement. And that way the siding can dry out from the backside if there's any humidity that shows up there because of wind and weather and rain. So I'm pretty happy with how that went together. There's a picture of the foil tape covering all the screw holes, covering all the seams, and I did my best to really be anal on that. And again, the guys that were working the job just said, "This is crazy. What are you trying to do?" So I knew what I wanted. I wanted a house that was so airtight when you close the door, your ears pop. Right. I wanted the ACH value that Dr. Bell has, and I didn't quite get there. But so here we are ready for siding with brand new windows, triple pane, argon backfilled, low E, with a double gasket seal. Also, I figured this is a major heat loss vector. So I spent $22,000 on windows and doors to replace all the existing. Now you can see the smart siding going up over the top of the battens, trimmed, caulked. It looks pretty nice from the road. So I had a blower door test done, and in the process of doing that, discovered some really major air leaks between where the wall and the rafters tied together, because it would have required perfect installation by people who were really dedicated and committed to doing that high-level job. These guys were day laborers. They got paid cash at the end of the day. Let's just say they didn't quite get there. So I ended up with a leakage rate of 165 cubic foot per minute at double the pressure. And now they were actually able to get it up to 50 Pascal. So I brought down my leak rate by an enormous amount. So I have an air exchange rate of 3.1 ACH, which is still way above what passive house would like. But in the process of doing this, we found some really, really major air leaks. So now I've gone and fixed those air leaks. And I'm disappointed to say I did not manage to get another blower door test done before I could come here and tell you what the final is. What I can say is that it is much, much, much warmer inside. I turned off one of the 4 burners in the furnace, so it's only running at 3/4 of its original capacity. I reduced the blower setting. I've got an old furnace again, manually wired 3-speed motor. I'm running it on its lowest blower setting, and the duty cycle of the furnace is probably down to like 30%. And doing all the work with the high-speed blower and all 4 burners on, I was running a duty cycle of probably, I would say, 75%. When it was really cold, it was on a lot. I also bumped the design temperature up. The interior, what's the thermostat set at? From 60 to 72. My wife's much happier. If you're ever going to do any kind of building science and home design stuff, you want to ask the ladies, is it warm enough? Because all the men are going to be wearing t-shirts and the ladies are going to be wearing sweaters. So we're a good 10 degrees warmer inside the house, in addition to having much lower leak rate. So this is what got done to mitigate those two major leaks. I had isocene foam blown in from the inside because I just could not get to the leaks from the outside. So I've got 4 inches on the roof deck and an additional 6 inches on the gable ends. And they also really paid attention to the outside perimeter edge of the roof to catch that seam between the walls and the roof. And it looks like they've caught it because there's no more. I had condensation issues on the exterior, and that has stopped. So now I need to get the blower door person back in to do a final blower door test. For my air quality management, Zender is the big name. They are top shelf. They're very good, but I ended up going with somebody out of Urbana, Illinois, a couple of faculty that left the university there and started off their own company, Build Equinox, and they have a unit called the Serve 2 energy recovery ventilator. Instead of having a passive heat exchanger, this has a little mini split in it. So I can actually bump heat and or cooling into the air instead of just tempering what's coming in from the outside. Because if I'm exhausting 72-degree air out and I run it through a passive heat exchanger, I can temper the incoming air. But if it's 0 outside and I'm exhausting 72-degree air, somebody help me with the thermodynamics, right? So the incoming air ends up coming up to maybe 55 or 60. That's relatively cool to be sitting next to. With this unit, I can actually bring it back up to indoor air temp. So I can do about 6,500 BTU of heating. It can pump in 5,000 BTUs of cooling and actually pull 4 gallons of water per day of humidity out of the indoor air. Instead of just eliminating some of the humidity that's coming in from the outside, I can actually remove what's in the indoor air. The fans are continuously variable speed, dialing back down to 50 cubic feet per minute. That's about what you get out of a cooling fan off of a desktop computer. That's about 50 cubic foot a minute. Maximum is 250 cubic foot per minute. This has sensors in the exhaust going out that continuously monitor CO2, VOCs, humidity, particulates, and temperature. And it also has additional control options for running an external humidifier and or dehumidifier. It can manage additional heat pumps or backup heat. If I want to fire up the old propane furnace or I want to install electric resistance, this unit will be the brains that manages all of the indoor air quality. Yeah, so there's my wife. You can see the box is pretty big. We have a small basement. It was a bit of a challenge to figure out where to actually position the thing. It's got 10-inch diameter ducts going through the house walls. That was a bit of a project to figure out exactly where to locate it. But I'm pretty happy. We are close to getting it installed. So now I want to pitch some issues, some questions. There's a whole lot of design stuff that I don't understand. As Dr. Bell said, you know, he wanted help with how do you manage the system. Yeah, me too. So my goal, right, the question is, what is the answer? What is the proper question? And my proper question is, how do I lower my carbon footprint? I'm not necessarily interested in how long it's going to take to pay back the system. I want a small footprint, as small as I can do. Secondary goal, reduce the lifetime cost of the power. And then tertiary goal, stable power that's not grid dependent, right? Power failures, power price fluctuations. I'm on Energies, Wisconsin Energies in southeastern Wisconsin, and I'm on time of day rate metering. So I'm set for 7 p.m. to 7 a.m. for peak rates, and my peak rate is 27 cents per kilowatt. And my overnight off-peak rate is 10 cents per kilowatt. Anything that I generate, any surplus that I generate, Energies in its kindness and generosity is going to buy it back from me at 4 cents a kilowatt. So they completely eliminated any incentive to provide, you know, to do over generation. There's no way to pay back that cost. I did get a quote for a PV system, and I would love some help. This is some of the information that I got. For a 94% offset system, they're looking at $60,000 for panels. I need a pull mount system because I don't have enough roof line to install that many panels. That's an awful lot of money for PV panels. And that would be a grid tied system that does not include batteries, but it has battery management capacity. If I back down to a 45% offset, we're looking at $33,000 installed price. That's still a pretty hefty sum. I could use a little help figuring out what do I do here, right? Which of those two versions do I go with? Do I take the 45% or the 94%? What about a house battery? How does that impact my overall cost to live with it? Right now, I'm still on time of day rate as opposed to going to flat rate. If I have a PV system, does it make sense to get rid of time of day rate? Because then I'm generating peak power during the day. So I don't understand that. That's kind of above my pay grade. What if I install a house battery? How does that impact the fiscal calculations? Do I go back to a fixed metering or time of day rate? Load shifting. Right now, I'm running, the furnace gets set back at night. I have an electric car. I only charge that at night. Domestic hot water gets heated up at night. But if I go to a PV system and I go to flat rate metering, does it make sense to do load shifting? Yeah, I don't understand. Unfortunately, my car, I've got a Tesla and I don't have grid to home or car to grid or car to home options with a Tesla, not yet. So I don't have the ability to do any load shifting with the car. Next question, summer and winter temperature management. I need help figuring this out. My serve supplies about 5,000 BTUs of cooling. Manual J calculations, I ran two different versions. I did load calc and cool calc online. And they all have really serious fudge factors built in, none of which I can get to and tweak because that's all behind the web interface, right? But my predicted load, my cooling load is about 12,000 BTU at a 75-degree design temperature. If I use overnight ventilation to open up the doors and windows and cool the house down overnight, given average temperatures for my area, how much natural overnight cooling can I expect? How much can I pull the house down? I can supply roughly 12,000, roughly 5 of the 12,000 of the design load for cooling. Is that close enough? What if I raise my design temp to 80 degrees instead of 75? Can I get away without needing to do additional air conditioning? Right, that's my hope, right? If I'm just doing humidity management, and if I can live with 80 degrees instead of 75, maybe I can get by. The sneaky answer is for the last 2 years, we have gotten by without anything. We just open up the windows and I run a portable dehumidifier overnight, or actually in the morning after my wife gets up early, she'll shut the doors and windows. We'll run the dehumidifier for 2 hours to try to pull a little bit of water out and we're good for most of the day. It can get a little toasty by the end of the day, but I'd be curious to have some help figuring out, do I need to plan for additional cooling? What about winter management? The serve will put in about 6,500 BTUs of heat. The manual J predicts my total heat load is 27 BTU at 75 degrees design temp. I'm consuming 550 kilowatts inside the thermal envelope on an average month. That's quite a bit of heat, right? I mean, that's heat line power, the refrigerator and microwave and all the rest of that. That's dumping heat into the building. If I get some help converting that electrical consumption into heat, and then I add that to what the serve can supply, how close am I to meeting my design temperature? Do I actually need a mini split to be able to stay warm over the winter? If I do, right, if I can't manage to do it in the coldest, how much wider is my shoulder season where I don't need to supplement any additional heating or cooling, right? By one metric, you should design, in theory, you should design the heat pumps to only be able to provide you heat up to 80 or 85% of your design load. Because otherwise your equipment is oversized. And when you get to that design load limit, well, then you supplement with whatever electrical resistance or backup forced air. How much bigger are my shoulder seasons? I don't know. Here's another problem. I committed heresy and I bought an electric resistance water heater instead of a heat pump water heater. So I have a brand new 45-gallon, 5-kilowatt water heater to replace a 22-year-old water heater that never gave me any problems. It was actually the flexible connection going into the plumbing that ultimately failed. But I had a mechanical time clock that was running it. So I upgraded to a new Rheem, which is Wi-Fi enabled, geo-fenced, So it turns down whenever I leave the house. I don't have to remember to turn it down. But it's still a 5 kilowatt water heater. Install cost of 800 versus a heat pump water heater of 1,700, right? I did the install. So the question is, if I were to go to a heat pump water heater, what's the mean free time between failures? Right? How long before I get a service call for my heat pump water heater, which I doubt I can service myself, right? But with an electric water heater, I can go to the hardware store and buy a 5,500 kilowatt, 5,500 watt element for $30, and I can install that myself. It needs a screwdriver and a wrench. What's the expected service life of a heat pump water heater? This is part of why I went with the old version, because I'm seeing, at least online, everything on Reddit is true, so I know that to be a fact. But a lot of people have issues with the longevity, the service life of heat pump water heaters. If I have to call in a service tech, well, what's my baseline cost? What's the average cost to repair a heat pump water heater versus an old school electric resistance water heater? And all of that boils down to what is the cost to own per BTU for hot water over 10 years of operation for the two versions, a heat pump versus the old school electric resistance. So now I'm coming to the conclusion to try to coax some of you into going into this field. Where are all the engineers with the appropriate design skills to design an integrated system, which is a house that's built to kind of contemporary standards? There are very few and far between. They're difficult to find, even at the place where maybe money is less of an issue. There just are very few. There are some architects here and there, but that's all. I'll keep going. So, but there are millions of homes out there that need renovation. And who is going to help do that kind of renovation design work? We need mechanical engineers who are able to come in and offer support to builders and contractors, because they are not interested in going outside of the middle of the bell curve. They want to land in that 80%. Nobody wants to be on that 10% margin, which is significantly where this house is. A contractor never, ever wants a callback. They want to see me when they're done and never, ever again. So if we're going to try to move building codes forward and building design forward at more than a generational exchange basis, we got to get people out in there into the field, maybe hopefully folks like you that can help educate and train contractors to help them feel a little more comfortable about trying something that's non-traditional. Thank you. I don't know if we have time for questions anymore. I can field them via email.
Yeah, unfortunately, we need to vacate the room. There's another class that is coming into our improvised room here. But thanks so much to both of our speakers. I thought that, at least for me, that was super interesting. And I have the coolest job. I can learn from folks like this. And so maybe we can follow up via email if needed. And then folks who are here in the room, we can ask questions with Erich, maybe like outside or in a different room. But feel free to take off if you have another thing to get to. So thanks, everybody.